So here we have the necessity, we feel the need of ways to represent an organic compound, because we must know what is the nature of functional group that is present in a molecule. We must know what is the nature of bonding, what is the order in which the atoms are connected with each other, right? So that becomes very important to have an understanding of structural representation of elements or compounds in a useful manner, right? So by drawing a structure for any organic compound, we will be determining the arrangement of atoms, and the arrangement of atoms will help us in predicting the physical and chemical properties of any organic compound, right? So we can represent organic compounds in a number of ways when it comes to their structure. So these different ways in which organic compound can be described includes the Lewis formula, the Kekulé formula, condensed formula, Bond-line formula, and the Polycon formula. So all of these are useful depending on what is our need or how much we conveniently feel in using these formulas. So firstly, we will consider about the condensed structure formula. So condensed structure formula is actually made up of elemental symbols, and the order of the atoms suggests their connectivity. So this is here, for example, this is structure of an ethanol. So here you can see that we have CH3 joined with CH2. So here it means that carbon and carbon are bonded together. So in condensed formula, we don't make use of any dashes. So this is the sequence. This carbon has 3 hydrogens bonded to it, and this carbon is further bonded to a carbon, and this carbon has 2 hydrogens further bonded with an OH. Right, so this is the sequence, and the sequence suggests the connectivity, right? But the problem is that if its structure is more complex, then we cannot describe its condensed formula, right? It becomes often difficult to interpret the structure. So as the structure becomes more complex, that becomes difficult to understand the connectivity. Just for example, consider this structure. So we have chlorine bonded with CH2, CH2 bonded with CH2, then we have CH, and here we have this bracket. So whenever bracket comes, understand this is a substituent at this position. So there is O methyl group attached with this carbon here, and there is a methyl, right? Similarly, we have methyl here. This is bonded with NH, NH with bonded with CH2, and CH2 bonded with carboxylic acid. Alright, so condensed formula becomes difficult when the structure of a molecule becomes more complicated. Further, you cannot draw the condensed formula for cyclic compounds. And if you have larger, more complicated formulas, then you cannot also draw the condensed formula for those compounds, right? So in condensed formula, the role of parentheses is very important. So how? One thing is that if you have a long chain of identical groups, for example, you are seeing that this CH2 group is repeating a lot number of times, right? So what we can do in order to make it convenient and easy for us to write the condensed formula, so we count the number of times this CH2 group is repeating. So this is repeating 4 times. So what we do, we write this methyl, then we put the brackets here and put CH2 inside, and outside it we write the number of times the CH2 is appearing. So we write CH4, right? So this changes to this one. So that becomes more convenient and more easier to write this condensed formula instead of repeatedly writing CH2, CH2, CH2 here. Similarly, we can also make this structure formula brief. So this condensed formula has a lot number of CH2. So it has 6 CH2s inside here. So in order to make it very easy to write, so we can put the brackets here, put CH2 inside, and 6 here. So 6 indicates that CH2 is repeating 6 times. Here also we have CH2 that's repeating 5 times, right? The parenthesis is very important because it helps us in writing the condensed formula in a more easy and a more quicker way. Also, position of certain functional groups can be represented by parentheses. For example, here, so here we have wrote this chlorine inside the brackets, so that indicating that chlorine is attached with this carbon. Similarly, we have hydroxyl here, and if you can see, there is 2 outside this bracket. It means to this carbon there are 2 hydroxy attached here. Similarly, here we have a carbon, and with the bracket we have methyl, means methyl is attached with this carbon, and here we have CO. So CO, whenever it's written, it means that's a carbonyl group, right? So whenever you have CO written like that, just understand that's a carbonyl group, and this carbonyl group is attached to this CH2 and this CH2, right? So that means that's a ketonic group. So condensed formulas can be written, and they can be easily written by means of using the parenthesis, right? So condensed formula give us the sequence of atoms, but however, if you have very complex structures, if you have large structures, if you have cyclic structures, so we cannot write condensed formula for them, right? So it becomes very difficult to understand the condensed formula when the molecule becomes much more complex. So next we have another way of writing the structure formula, that is the Lewis structure. So Lewis structure is a very simplified representation of valence shell electrons in a molecule, right? And this shows how the electrons are arranged around individual atom in a molecule. So normally we make use of electrons as dots, or you may use bonding electrons as a line between two atoms. If you have a single bond, we write single dash. If you have a double bond, we write double dash. If we have a triple bond, we write triple dash. In case of the condensed formula, we were unable to write the single bond or double bond or triple bond. We just saw how many atoms are attached to the carbon, and then we predicted whether the bond is single, double or triple. But the Lewis formula has the advantage that it can show the single bond, double bond or triple bond, right? So you can show the bonding electrons as dots, or you may also use lines for indicating the electrons. So lone pairs may or may not be shown. So if they are shown in the form of two dots on the atom which has the lone pairs. Right, so that's a very popular way to depict the structure of an organic compound. However, when the size of a compound increases, it becomes very difficult to use the Lewis structure. Right, so that's why although Lewis structure is very important, but we have devised some other structure representations that are more helpful in representing the structure of a molecule. Now we have straight line formula or Kekulé formula. So Kekulé formula and Lewis formula, they are almost the same. The only thing is that the covalent bonds are represented by dots in Lewis formula, but they are shown by line in a Kekulé formula, right? So Kekulé formula are also known as Lewis structure. So there is very slight difference. So normally both are considered as the same. However, if you have to differentiate between the two, just know that if the bonding electrons are shown by dots, then that's the Lewis formula or Lewis structure. But if the bonded electrons are shown by a line, then in that case this is known as a Kekulé structure. So Kekulé structure is also known as straight line formula. Right? So lone pairs are indicated as two dots here, and sometimes they are left out. For example, here in this chlorine, we are not showing any lone pairs, although they are still there, right? So you may show the lone pairs, or you may prefer to leave them out. That depends on what is your preference, right? So this is the way of writing Kekulé formula. So this is a Kekulé formula. You can see whenever there's a lone pair, we are representing them as two dots, and whenever there's a bond, so that's represented by a line. Right, so normally Kekulé formula and Lewis formula are considered the same. There are very slight difference between them, but most of the times people consider them as the same thing. Right, just for example, we have drawn a Kekulé or Lewis structure for retinol. So retinol is a very common form of vitamin A, right? So this is a structure. See, this structure is showing you the presence of double bonds, and there's an OH with lone pair of electrons, right? And there are methyl groups and hydrogens here. The structure is very detailed, so you know which carbon is attached to which with a double bond, where there's a methyl, where there's oxygen, and oxygen is having lone pair. The structure, although, is giving you much more detail about the structure. However, when you see this structure, you become confused at the first sight, because it's very difficult for you to interpret. It's showing a lot of hydrogen atoms, and it becomes very difficult to compare overall structure of this molecule with a structure which is similar to it. If there is a formula, if there is a structure which is very similar to this structure, that will be becoming very difficult. That will become very difficult to compare the two structures. Also, from seeing the structure in the first sight, it becomes very difficult to focus on the double bonds here, right? The double bonds are very much eclipsed. They are trapped between the hydrogens, and the first thing we see and the prominent thing we see in these structures are just the hydrogen atoms, right? So the presence of the lot of hydrogen atoms is making it very complicated for us to understand this Kekulé structure. So this is the limitation of Kekulé or Lewis structure, that although they give the detailed explanation about structure, but having a large number of atoms, especially hydrogen atoms, it becomes very difficult to focus on a functional group or double bond if there are a large number of atoms. Also, if the structure becomes more larger or more complicated, writing a large structure by means of Kekulé formula, that becomes very difficult, and the chances of errors very increase a lot. So in order to eliminate the problems that are associated with this Lewis formula or Kekulé formula, line formula were devised. Right, the line formula are also known as the skeletal formula. They are also known as bond line formula, or they are also known as zigzag formula. Why they are called zigzag? Because the line appears in the form of zigzag manner. The Kekulé structure, also known as straight line formula, because if you see the structure, all structures are presented in the form of straight line, right? But these line formula, they are presented in the form of zigzag manner, right? So you can see that's in the form of zigzag manner. That's why they are also known as zigzag formula, or they're known as bond line formula, or they're known as skeletal formula, or simple line formula, right? The advantage of this formula is that we don't show all atoms here. The only atoms we show are the heteroatoms, right? So we don't show any carbon atoms, we don't show any hydrogen atoms. Hydrogen atoms are only shown if they are attached to some heteroatom. Right? So what's a heteroatom? Heteroatom is an atom which is other than carbon or hydrogen. Right? So hydrogen is only shown in the line formula if the hydrogen is attached with some heteroatom. For example, here you can see there is no hydrogen, there is no carbon, but here we have an oxygen, and to this we have a hydrogen attached here. So how we represent the structure? So at the end of each line, so if you see here, this is known as the terminal, and this line is known as the intersection here, right? So this is our terminal, and this is the intersection. So each terminal has, we say this is actually representing a methyl group here. Right, so whenever there is a terminal like that, it means there is a methyl group. Similarly, there is a methyl group, and whenever there is an intersection, it has carbon. So intersection means there is a carbon, and you just count the number of bonds to this carbon. So it has three bonds. The fourth bond will be with hydrogen. So it means this structure has a CH here, a methyl here, and a methyl here, right? So these structures are easy to represent here. Now we have another formula. So you see this is a Cl, so chlorine is dash 2. So this is intersection. So at intersection we have carbon. So just see carbon is forming 2 bonds, and those other 2 will be hydrogen. So there are 2 hydrogen attached here, right? So we are not showing the carbon because it is always appearing as an intersection here. Similarly, we have also carbon at this intersection. We have also carbon at this intersection. Just count the number of bonds, and in order to make the valency up to 4, so just add the hydrogens which are missing. So we have to add 1 hydrogen, so valency of carbon is satisfied here. So again, this is the terminal. So this methyl is terminal, so it has, since it's terminal, it has methyl group here, right? And since it's also terminal, so we have methyl group here. So in this way we can write the line formula and zigzag formula. So this is a line formula for benzene here. Again, you're saying that we are not showing any carbon, we are not showing any hydrogen. So this carbon, you can see this is the intersection, right? So this is a carbon here, and this carbon is forming 1, 2, 3, 4. It's forming 4 bonds already, so you don't need to attach any hydrogen. So this carbon is forming 1, 2, 3 bonds, and the fourth one will be hydrogen here. So similarly, you can add hydrogens whenever you want to attach hydrogen, right? So similarly, this is the terminal carbon here. So whenever there is a terminal carbon, you must know that actually the terminal carbon is a methyl group here. So this is carbon at intersection. So whenever there's this intersection, there is a carbon, so you can fulfill its valency. Similarly, this is carbon at intersection. So you can add just one hydrogen in order to complete its valency. This is also a carbon here, so you can just see that it is already forming 4 bonds, so you don't need to attach any hydrogen here. Right, so in this way we can write the line formula or the zigzag formula, right? So although we don't draw the hydrogen atoms, but we do draw the hydrogen atoms if they are connected with some heteroatom, right? Otherwise, if your hydrogen is not attached to a heteroatom, then there's no need to see that. So here is a bond line formula, right? So this is formula of retinols. Just compare this formula and just compare this formula. Both of these formula are representing the same compounds here, but see the ease with which you can easily see where are the groups. So you can easily see here are double bonds, the position of double bonds you can easily see. So these are the terminal groups. So whenever we have terminal groups, you can see this is actually a terminal. So this is a methyl here, similarly a methyl here, and also we have methyl here and methyl here, right? So these are the intersections. So you can add carbon to the intersection and predict its valency. So it's a very simplified representation, and also very easy to draw the structure, and we can draw the structure with in a very quicker manner than the structure that was represented previously. Right, so bond line formula are quicker to draw, they're easy to draw and easy to understand as well. Right, so there are, okay, so we write only the heteroatom in case of the bond line formula, right? And terminal denotes the methyl group. So here I've just drawn the structure for your ease of convenience. You can see here. Then we have a terminal here, right? So whenever there is a terminal, you should know there is a methyl group here, right? So there is a methyl group here at the terminal. So we have methyl whenever there is a terminal, and there is an intersection or line junction. So whenever there is a line junction, you should know that at line junction there is a carbon, and you have to just count the bonds of this carbon. So this carbon is forming 2 bonds, and 2 more will be hydrogen. Similarly, this is also line junction. So at this line junction we have carbon, and you can satisfy the valency by adding sufficient number of hydrogens in order to make the valency of carbon up to 4, right? So here we have function group here, right? The bond line formulas are very easy to draw, they're very easy to understand, and that takes very less time, right? And the chances of error are very less in the bond line formula. Also, there is a very advantage in this formula that instead of writing a terminal, if you have any confusion, so you can even write methyl here. So instead of writing ME, you can write a ME. Instead of writing CH3, you can write simple ME. So ME stands for methyl, right? So whenever you're writing a formula and you just get confused into a terminal carbon, so what does that terminal carbon indicate? Just write a methyl here, right? So whether you write a nothing here, that still means a methyl group. If you write a CH3 here, that means there's a methyl group here, right? Or instead of writing that methyl in the form of CH3, you can simply write ME here, right? So whether that's CH3, nothing, or methyl, all of these mean the same in case of bond line formula, right? They're very easy, they're very quick, and it becomes very easy for us to understand the structures when we use the bond line formula. Right, cyclic compounds which were previously not be able to be represented by condensed formula, they are easily represented by bond line formula. Right, so you can see this is a bond line formula. So this is bond line formula for cyclopentane. You can see this is CH2 here, CH2 here, CH2 here, CH2 here, CH2 here, right? So all of these are CH2 in the form of 5-membered ring. So when we are going to write the bond line formula for it, we just eliminate all of the carbons and we'll eliminate all of the hydrogens, right? So this is the formula, but when we are writing the bond line formula, so we're writing like that, right? So in case if you want to draw a substituted bond line formula, then in that case you can just like this one, right? So this is a terminal carbon, so it means you have attached a methyl here, right? So if you want to make a double bond, so you can have a double bond here. If you want to have a ketone, so you can have a ketone here, right? So when we are writing terminal, so we don't need to write a methyl or anything, but if you are still confused, you may prefer to write it like that one, right? So you can write it this way. So cyclic formulas, whether they're complicated, they're not complicated, whatever, you can easily write the bond line formula for them as well. For example, I'm just writing a bond line formula for a molecule that has two cyclic systems attached, right? So it has two rings, and see if you can understand what does that mean, right? So this is bond line formula for a compound, and it has two rings. It has a 6-membered ring. You can count them: 1, 2, 3, 4, 5, 6. It has a 6-membered ring, and the 6-membered ring is attached with a 5-membered ring here as well. So just in a very short time I've drawn this structure, and you can add a number of substituents. You can add any functional group you like. So if you see here, I've attached a carbonyl carbon. Here I have attached a methyl group. Here I have attached a carbon-carbon double bond here, right? So, and you can bring any substituent, whatever be your preference, in a very short time and in a very easier manner. So bond line formulas are the most ideal formula representation for organic compounds. So the next type of formula that are normally used are the polygon formula. Right, the polygon formula are only used for organic compounds that are actually joined in the form of a ring, right? So the polygon formula cannot be written for organic compounds that are in the form of chain. So polygon formula are only for the organic compounds that are in the form of ring or in the form of cycle, right? For example, you can see there we have cyclic system. We have a benzene ring here, right? So these are substituents on the benzene ring, right? So in polygon formula also we don't show any carbon or we don't show any hydrogen. We just show the pi electrons. So all the sigma bonds are represented like the straight lines, and if there's a double bond, we just draw a double line here. So there's no need to show carbon or there's no need to show hydrogen. However, if you have some heteroatom attached, then you can write the heteroatom just like you have written in the bond line formula, right? The only difference between bond line formula and the polygon formula is that the polygon formula are only written for cyclic system. Right, so if you have a cyclic system, then you write a polygon formula, but if you have a chain system, then you cannot write a polygon formula, right? So these are polygon formula for different isomers of disubstituted benzene. So this is 1,2-dimethylbenzene, 1,3-dimethylbenzene, 1,4-dimethylbenzene, etc. Right? So here we have some other examples of the polygon formula, right? So in polygon formula, the coordinates of a polygon, so these are the coordinates of polygon, they represent carbon, right? And this is a side, if there's a side chain, it's a side carbon-carbon bond, right? So this is this coordinate that's indicating carbon, and this line is showing the bond between carbon and carbon, right? So in case if you have some other heteroatom, in that case, right, then we have that heteroatom represented. Otherwise, the heteroatom will not be represented. So this name of this molecule will be methoxycyclopentane, right? So there's some error in the name. So this is methoxy. So the name is actually methoxycyclopentane. Right, so you can put any heteroatom anywhere you like in this polygon formula, and it's very easier to use, right? So just like in the bond line formula, so this is terminal carbon. So this terminal carbon that is showing you this is indicating the presence of a methyl here. So again we have methyl here, right? And this is the corner of this polygon. So when we say corner, so corner representing a carbon, and this line between this carbon, this line is showing the bond between carbon and carbon, right? So if you have a double bond here, so we write this like that one, right? If we have a single bond, just represent it like that one. If you have a triple bond, that will represent it like this, right? So there's no need to show any carbon, there's no need to show any hydrogen. If there's a heteroatom, you can show that a heteroatom in this molecule in a very nicer way. So polygon formula are also very quicker way, right? So the polygon formulas are just like the bond line formulas. The only difference is that polygon formula are only for the cyclic molecules, but the bond line formula can be written for cyclic molecules as well as acyclic molecules. So they are almost a similar thing. So far we have discussed about the chemical formula. The chemical formula don't give any information about structure or the functional group or the connectivity. Then we saw about the condensed formula. The condensed formula gave information about the connectivity, but they didn't give much information about the structure of a molecule, right? Furthermore, when we have a complex structure or a long structure, so it becomes very difficult to write the condensed formula for it. Also, we cannot write condensed formula if a molecule is cyclic. So condensed formula are useful, but they are not much useful when you are interested in representing the structure. So the other way is to write the Kekulé structure or Lewis structure. You must know the slight difference between the Kekulé structure and a Lewis structure, right? Both are almost same, but if you are representing the bonded electron in the form of dots, this is known as the Lewis structure, and if you are showing the bonded electrons like a line, then that's known as a Kekulé structure, right? So both show the presence of a functional group, both show presence of lone pairs, both show the atoms connected in the form of a linear manner. The Kekulé structure also known as straight line formula, right? So however they are very easy, however they represent the structure very easily, but the problem is that when the molecule become very complicated or very large, then it becomes difficult to write the formula, and also it becomes very confusing to interpret the structure, because as the molecule get larger and more complex, the number of hydrogen and carbon increase, so it becomes very difficult to understand the molecular formula in that way. So instead of using the Lewis formula or the Kekulé formula, we make use of the bond line formula, which are also known as zigzag formula or simple line formula, right? So why we are saying that zigzag? Because the bonds are drawn in the form of zigzag manner. So whenever there is a terminal carbon in a line formula, that is indicating always a methyl group. So we don't show hydrogens and methyl in a bond line formula, but however if a heteroatom is present, the heteroatom is shown, and if hydrogen is attached with the heteroatom, the hydrogen is also shown here. Then we saw the polygon formulas. Polygon formula are just like bond line formula. The only difference is that polygon formula are only used for the cyclic molecules. If your molecule is not cyclic, you cannot draw a polygon formula. So in polygon formula, the corner of polygon, they are indicating presence of a carbon, while if there is a terminal carbon like that one, that indicates the presence of a methyl group here. So we can show the presence of heteroatom here as well, just like in case of bond line formula. Right, so that's all about the structure representation of organic compounds. So all the line formula are easier, more convenient in expressing the structure. So knowledge of all of the formula are also very essential for understanding the chemistry. Right, so that's all for today. I hope you have understood it well. Thank you.